So we've now talked a lot about electric fields and how they apply forces to electric charges that are placed inside of them. And we've also talked about electric potential and how that helps us categorize at every point surrounding some source charge in the electric field, how the system will gain electric potential energy if another charge is placed inside. But how exactly can we connect the two? Well, first, let's quickly go into a little bit of detail about how we visualize electric potential. Because like electric fields, we cannot physically see it, so typically it's represented through what are known as equipotential or isopotential lines. Iso meaning same, and these are lines where every point on the line has the same electric potential in volts. So for instance, I have this positive charge here and this negative charge, and around them we've got circles, these rings of these dashed lines, which are all equipotentials. And we notice near the positive charge, those are positive electric potentials, and near the negative charge, those are negative electric potentials. And near the positive charge, as we get closer to it, we've got bigger electric potentials, so like, for instance, plus 4 volts. So every point on this line would have an electric potential of 4 volts, then 3 volts, then 2 volts, and then 1 volt. Keeping in mind that these are arbitrary values. We didn't do any sort of calculation here. This is just for a demonstration. And for a negative charge, it would be the opposite effect. We would have -6, so a big negative electric potential nearby, and then we would get smaller, -4, -2, and even go to 0 as we travel further and further outward. Now, something else we want to make sure we remember is that if we travel along these equipotential lines, there is no change in electric potential, so there is no voltage, and therefore there is no change in electric potential energy, and no work is therefore needed. The same thing would be true if we moved from one equipotential line to another with an equivalent value. So if I started, for instance, here on this -2 volt line, and I moved to a different equipotential with -2 volts, then the total work required would in fact also be 0. So this is how we typically visualize electric potentials. And if we want to look at the electric field at the same time, we can go ahead and draw electric field lines on top of these, remembering that electric field lines are lines that show the direction that a positive test charge would follow if placed in the field. So if I look at the positive charge here, well, a positive charge would move away, so the arrows point away. If I look at a negative charge, the arrows point towards it because a positive test charge would move towards it. And we can see that they go radially outward from these two charges. And we can already start to see some connections between the electric field lines and the isopotential or equipotential lines. But let's look at a couple more examples and it'll really become crystal clear. So the other way we visualize electric potential are through what are known as equipotential surfaces. These are 3D surfaces that help us visualize the electric potential at every point surrounding some system of charges. So, for instance, going back a step, this was the equipotential or isopotential lines. And if I want to visualize these as surfaces, what I need to do is I need to visualize, I'm going to basically take these and I'm going to rotate the system so that instead of looking at them from like a bird's eye view, we're going to look at them so we can make the equipotential lines more in level with our eyes. So I'm going to rotate those, and in doing so, we end up with something looking like this. So if I look at these two diagrams, if I was to look at them from above, it would look exactly like we just looked at. But now what I see is with this positive charge, I create kind of a peak in the electric potential, and negative charge, I kind of create a valley in the electric potential. And in fact, this is a very, very useful analogy that when I'm looking at these sorts of things or looking at these sorts of graphs, I can think to myself, okay, positive charges are like a mountain and negative charges are like a valley. Now, it's just an analogy, but it's a useful one. And additionally, that means that all of these electric potential lines, these specific equipotentials, are really just telling us elevations. So if I look, for instance, at this positive charge, this has a very high electric potential here, and as we go further down, we go 4, 3, 2, 1, it would eventually even go to 0. And on a negative 1, we start at 0, and then we go -4, -4, -2, -4, -6, and then have a very high being relative, negative electric potential down there at the bottom. Now, going from here, though, if we were to redraw these electric field lines on these surfaces, well, they're going to look exactly like they did on the previous electric potential lines. So if we were to look at them from above, they would just go out radially. But when we look at them from the side here, we could see that they basically follow the curves of these slopes. So for a positive charge, it would go down the slope away from this positive charge, and for the negative charge, they would go down the slope into the negative charge. And so for the sake of this analogy, the electric field lines are really a path that if we put a positive test charge ball, so if I had like a little positive ball and I put it on there, on this positive side, it would just roll down the slope, because that would be how a positive charge moves away from positive. It is repelled. And so we can imagine it as, okay, it is a positive charge, and it's kind of like it's going down the slope as it's repelled. And similarly, this analogy extends to the negative, that it's going down the slope towards the negative. Once again, this is just an analogy that helps us visualize the situation, but it makes it much, much easier to process how the two connect together a little more formally. So how can we more formally connect electric fields to electric potentials? And right now we're really focused on the directions of the lines and the directions that these are going to go. So let me go ahead and bring up two situations here. One is going to be two positive charges, so two like charges, and the other one's going to be a dipole, so a positive and a negative charge, two unlike charges. And let's go ahead and draw the equipotentials around these. Now, let's look at these here. So on this left-hand side, we have nearby some very high positive electric potentials, or higher, and then as we get further out, they go out a little more, and then you notice that eventually we reach a point where the electric potentials from the two combine. Because if we were to zoom way, way out, basically these two charges, if we were zoomed way out, would essentially act like a single charge. It would make sense to eventually reach a point where we're just going to get rings of electric potential going around them. And to help us visualize this, we can think of this as, okay, this is two positive charges. I can treat these like two mountains. So two mountains with slopes that go downward on every side of them. Similarly, on this other side, I have a positive one here and a negative one here. And I actually should fix this. That should be a positive 1 volt, not a negative 1 volt. There we go. So I have positive, negative, and we have a zero line in between. So if I was to imagine these as elevation, I would say, okay, I've got like a mountain peak here with plus 3 volts, then plus 2, then plus 1. This would be kind of ground level, and then it's going to start dipping into this valley. You notice they don't share equipotentials because it's positive equipotentials around the positive, negative around the negative. We have to have a zero line in between the two. So if I was to visualize the electric field lines, let's first look at this diagram on the left. Well, imagine I have a little positive test charge. It's going to be repelled from both of them, and it's going to travel in such a way as if it was a ball rolling down these mountain slopes. So if I start doing that, I start getting something like this. On each side, it basically just goes straight out. Even really on the top and bottom, it does that. But when we go to the middle, it's going to start going at this angle, because if it started going here, well, that's not going to happen. It's going to basically sweep outward. Now, additionally, let's look at the negative side. And if I draw some electric field lines here, it would be like if I put a positive test charge ball near the positive, and I see all the paths it went around this entire system. And so a lot of them are just going to go straight in. It's going to basically roll down the slope into this valley of negative electric potential. And that's going to be what's happening on all of these points here. And if it's coming from this direction, it would just go into the valley. And if it was leaving this direction, it would just move away from the mountain peak. And if we look at these two diagrams, they match the electric field lines we've drawn earlier for a dipole and for two like charges. So this matches up. And let's start talking about a few trends that we notice that help us draw these lines in relation to each other fairly quickly. Well, first off, electric field lines always point toward decreasing potential. And by decreasing, we mean more negative. So if it's around a positive charge, it's going to move away. It's going to go from high positive to lower positive and eventually to negative. And if it's negative, it's going to go to more and more and more negative, which makes sense because positive charges are repelled from positive and attracted to negative. Secondly, and this is really, really crucial, electric field lines are always perpendicular to equipotential lines. And as we can see, we've actually done that here. That if I look at these equipotential lines, every time an electric field line passes it, it's at pretty much a perfect 90-degree angle. That is a really, really useful way to be able to draw these fairly easily, is because if I'm going from, for instance, this point, I have to constantly be perpendicular between all of them. If I'm not perpendicular, then that is not accurate. And lastly, electric field is stronger where the change in potential is more, for lack of a better word, sudden, where it happens over a smaller amount of space. So for instance, let's look at this region here. So let's call this region right here region 1, and we'll call this region out here region 2. Well, if I look at the two of these, if we looked at the electric field lines, we know for a fact that the electric field is stronger here because these electric field lines are more dense here than at 2. And if I look at the electric potentials, we see that the isopotential lines are more dense here than they are here, which means that there is a greater change in electric potential here than there is electric potential here. So for instance, this is just going -2 to -1. This is going, +3, 2, 1, 0. It's a real quick change. And to help us visualize that, how we can think about that with our mountain and valley analogy is that if you have a greater change in electric potential, that's a greater change in elevation. In other words, this would be an area with a steeper slope, and the ball is therefore going to travel faster because there is a greater change in the elevations. So the previous page was talking about how can we compare the directions of electric field lines and equipotential lines, which is that are always perpendicular, and electric field lines always go in the direction of decreasing electric potential. But how can we compare their magnitudes? How do I know how big one is compared to the other? Alright, so let's go ahead and start thinking about that now. And let's start off by trying to think through this by looking at a somewhat simplified situation. So let's say I've got basically two conducting metal plates with opposite charge. So one has plus Q, one has minus Q, and their distance r apart. This is essentially a charge capacitor, meaning that one side has all of one type of charge, the other side has all of another type of charge. Now, first off, I know that the electric field line in the middle between these two plates is uniform. We've already talked about that the electric field line really just stretches from one to the other, and at the edges we have these edge effects, but we're not really that concerned about here. We're going to look specifically in the middle at this uniform electric field in the middle. Now additionally, if I look at that, well, remember we just discussed that electric field lines and equipotential lines have to be perpendicular. So if that's the case, my equipotential lines will need to be going straight downward. In this region, they curve a little at the edges due to this edge effects, but in this region, they're going straight up and down, which makes sense because if this capacitor was, for instance, connected to a battery, we would know that the voltage on this side would be plus V, the voltage on this side would be minus V. I know we have not learned a whole lot about capacitors yet. That will come in time. And if we look at that, we know that these will have to change from plus V to minus V, and additionally, we know they must be evenly spaced. And why do we know they must be evenly spaced? Because this is a uniform electric field, and as we just discussed, the electric field line kind of goes along with how densely spaced the lines are. If it is basically constant all the way across, we should have a constant change in energy all the way across as well. But we're going to look at that in a little more detail to help us think about that. But additionally, let's say, to try to formalize this, let's say I put some positive charge here, Q, right next to the negative plate. Now, it's naturally just going to want to stay there because it wants to go to the negative. So if we want to push it to the other plate against the electric field, well, we're going to have to do some work. We're going to have to do work pushing it from that spot near the negative over to the positive. And that work will be equal to the change in electric potential energy. By pushing it across, we are storing electric potential energy in this system. Now specifically, if I look at this, well, what is an equation I know for work? An equation I know for work is the force times the distance. And we would be going against the electric force, and the distance is some distance r, so this would just be Fe times r equals delta UE. Now let's take this a step further. How can I categorize the electric force in terms of the electric field, and how can I categorize the change in electric potential energy in regards to the change in electric potential or voltage? Well, we know two equations. We know that Fe is QE, and additionally we know that delta UE is Q delta V. So let's just plug those in. So I have QE times R is equal to Q delta V. I just substituted in for these values, and I can see that since Q here is the charge placed in the field, I can get rid of that, and I'm now just left with E times R over delta V, and specifically we see that the electric field should be equal to the voltage over this distance R. And in fact, this is an equation that we want to know, that the absolute value of the electric field is equal to the absolute value of the voltage over the distance between 2 points. Now, let's be careful here. There's a couple of really crucial things. So we're looking between 2 points in particular. So that's the voltage between those 2 points. That's the distance between those 2 points in volts and meters. And additionally, this is the average electric field between the 2 points in newtons per coulomb. As we just saw, we derived this from an area with a uniform electric field. So in that case, the average is going to be equal to one value, so works perfectly fine. But if we're looking at something that is not a uniform field, it's just telling us the average electric field between those 2 points. To get a more accurate value, we'd have to go a little bit more into calculus and things like that. Now, additionally, we have the for instance, the absolute values, because remember, delta V could be positive or negative, and E can also be positive or negative, but really we think of it as having directions like right, left, up, down, whatever. So we're just going to get rid of the negatives, and we're just going to have to evaluate what direction the electric field goes based on our particular setup. Lastly, one thing I want to point out is if you look here, the units are newtons per coulomb, and over here it's volts over meters. And the question is, does that work? Can we get 1 volt over meter, get to newtons per coulomb? Well, a volt is a joule per coulomb, and a joule per coulomb over a meter, well, that's the same thing as a joule over coulombs times meters. And a joule, if we remember, is a force times the distance. That would be newtons times meters over coulombs times meters. The meters cancel. And in fact, we do get newtons per coulomb. A-OK. So you can give electric fields in newtons per coulomb, or you can give it in volts per meter. They're the same unit. Really doesn't matter which way you go. So to conclude, let's kind of do a practice problem here. Let's say in an old cathode ray tube or a CRT television. So just to make sure you see what that is, just like this picture here, this is like an old style television, the big boxy ones. That is what a CRT television is. Now, it's how CRT televisions works is they literally accelerate electrons from the back of the television to the front, and that actually will cause there to be basically flashes of light on the screen, which ultimately make your picture. We're going to talk more about how these sorts of things work later, but that's the basic idea. So in this old cathode ray tube television, electrons are accelerated between 2 plates, one at the back of the TV, one at the front of the TV. And as we can see, for instance, in this particular situation, one plate is at negative 5,000 volts, one is at positive 5,000 volts, and this electron is accelerated, and the reason it hits the screen is it actually goes between these, it basically misses the plates, goes between them and will hit the screen. But these are 25 centimeters apart, and the question we have is, one, can we determine the electric field magnitude between these 2 plates? And 2, if this electron starts at rest, can we determine its final velocity as it basically misses the positive plates? Go ahead and pause the video, try this on your own, come back, let's see how you did. Well, hopefully you gave it a shot. Let's start talking about how we would do this. Well, first off, how can we determine the magnitude of the electric field between the plates? Well, this would be a uniform electric field in this region, so we can just use that average electric field value, which is, the equation is delta V over delta R, absolute value. Now I plug in for this, well, I've got the change would be final minus initial. The final was plus 5,000 volts. The initial was minus 5,000, so plus 5,000 minus negative 5,000 would be 10,000, divided by the distance in meters is 0.25, and we get a total electric field of 40,000 newtons per coulomb. Boom, done. Pretty simple. Additionally, though, it said determine the final velocity of the electrons. Well, we know that the electron's change in kinetic energy will be equal to its negative change in electric potential energy. So that electric potential energy has to become kinetic, and we can find that by just doing Q delta V. So how do I do to plug in Q delta V? Well, the charge of an electron is 1.6 times 10 to the negative 19 coulombs negative, and the change in voltage is 10,000 volts. Multiply all these together, and we get 1.6 times 10 to the negative 15 joules. And from here, we just use our kinetic energy equation, because the initial kinetic energy is 0, the initial velocity is 0, so even though it looks a little complicated here, I don't need to worry about this term at all, and I just stuck this in for V is going to be, therefore, when I rearrange it, the square root of 2 times the kinetic energy over M. 2 kinetic energy is 1.6 times 10 to the negative 15 joules, and M is the mass of an electron, which we can look up on our equation sheet, which is 9.11 times 10 to the negative 31 kilograms. Quite small. And we can see that over this 25 centimeter distance, it actually will gain a speed of 5.9 times 10 to the 7th meters per second, which is actually pretty darn fast. So what are our main takeaways for connecting electric fields and electric potentials? Well, first, can we visualize these equipotential lines and surfaces? So when we see these lines going around charges, they'll show us the electric potential at every point, and we can try to help visualize this by thinking, okay, if it's a positive charge, it behaves like a mountain, a negative charge behaves like a valley, and the positive test charge is like a ball rolling between the two. That can help us visualize this. Can we utilize that analogy, connecting equipotential lines to geographic contour maps? What I mean by that is, for instance, those elevation maps, that's basically what we've created here. Can we draw electric field lines and evaluate the relative electric field strength from a diagram with equipotential lines? One, remembering that the electric field lines would be the direction that this positive charge ball goes, and additionally that the relative field strength is shown by how close the equipotential lines are. If they're really close, you're going to have a stronger electric field. But then can we also calculate the average electric field strength in an area of changing potential? So I have some voltage difference, delta V, between one point and another. Can I calculate the average electric field between those points? Pretty easily by just dividing that voltage by the distance.